Hello, everyone. I'm Sam Kumar from UC Berkeley, and I'll be presenting JEDI, many-to-many end-to-end encryption and key delegation for IoT. This is joint work with Yun-Sung Hu, Michael Anderson, Raluca Popa, and David Culler, also from UC Berkeley. So devices in the Internet of Things collect privacy-sensitive data, and they often exchange this data via intermediaries in order to perform their function. What this means, however, is that if one of the intermediaries or one of the network links becomes compromised by an adversary, then that adversary can see the messages that are being exchanged in the system. So it's natural to use end-to-end encryption to protect data while it's in transit. I'm going to argue, however, that existing end-to-end encryption protocols aren't a great fit for large-scale IoT systems as they exist today. And the reason is that existing end-to-end encryption protocols like, say, TLS, assume a one-to-one form of communication where one principal communicates directly with another one. But if you look at the large-scale IoT systems that are out there, almost all of them use a different paradigm called publish-subscribe for communication. And I'll explain that as follows. So suppose there's a temperature sensor that's producing temperature readings that are being consumed by an individual and by a service in the cloud. The way publish-subscribe handles this is that there's an intermediate broker that actually forwards the messages. And at an API level, the temperature sensor produces its reading and publishes it to a resource. In this case, the resource is sodahall/atrium/temp. And each of the two recipients subscribe to sets of resources. In this case, the cloud service, for example, is subscribing to all the resources that begin with sodahall. And the reason for doing it this way is that the temperature sensor doesn't have to know in advance who the recipients are going to be. So it's a very nice separation of concerns. The sensor only has to worry about its temperature reading and the resource. So the overall system consists of many such principles, all of which are interacting with different resources. So a natural question is, okay, how do we do access control? How does the broker know who is allowed to subscribe to what? And there's a different mechanism that's typically used for this called decentralized delegation. And the way that works is that if there's some principal, say Alice, who has access to all the resources beginning with sodahall, what she can do is she can delegate to another principal access to a subset of those resources for a limited duration. And the delegation is transitive. So if this principal has some device like a light bulb, he can delegate access for an even smaller subset of resources for an even smaller duration so that the light bulb can perform its function. So decentralized delegation is actually a really old idea. It was developed in the late 90s and early 2000s. But it's since become the state of the art for access control in large-scale IoT systems because it very naturally matches the flow of permissions that you typically see. One final aspect of IoT I want to mention is that IoT devices are resource constrained. So if you look at the devices that participate in IoT, you can put them on a spectrum from more powerful to less powerful. And as you can see, they differ by more than 3 orders of magnitude in what they're able to compute. Now, the nature of IoT is that all these devices have to be able to communicate with each other. So an end-to-end encryption protocol for IoT has to work on even the least powerful end of the spectrum, the ultra-low power, deeply embedded sensors. So with this background, I'm going to present JEDI, which is joining encryption and delegation for IoT. And JEDI is an end-to-end encryption protocol that allows senders and receivers to be decoupled, as in publish-subscribe, supports decentralized delegation, and can run even on resource-constrained IoT devices. In other words, it works within the 3 constraints of IoT that I mentioned earlier. So the bulk of the talk is going to focus on how JEDI works, in particular how we handle encryption in the new model with publish, subscribe, and decentralized delegation, and how we can make the scheme lightweight enough to run on resource-constrained IoT devices. So how do we encrypt something in JEDI? So first, the temperature sensor produces a reading. It labels it with the resources being published to, and then the question is, OK, how do we actually encrypt this? And the way typical end-to-end encryption protocols would work is that you encrypt using the public key of the recipient. But the whole point of using publish-subscribe here was so that the sender of the message doesn't have to know who the recipients are. So we don't actually know whose public key to use to encrypt this message. So our idea to get around this in JEDI is that we encrypt the message according to the resource to which it's being published, not according to the recipient as you would do in most end-to-end encryption protocols. In this case, the resource is sodahall/atrium/temp. So we're going to somehow derive from this an encryption key that we use to encrypt the message. Similarly, the recipients are subscribed to sets of resources, so they also have some resource-specific decryption keys that allow them to decrypt messages published to those resources. So now once we have done this, we can send the message to the broker. The broker reads the resource name and forwards it to the appropriate recipients, who can then decrypt the message using their keys. So what this means is that in the overall system, messages are encrypted with the resource name. So an adversary who controls the broker, either because the broker has been hacked or because the broker is malicious, cannot see the contents of messages that are being exchanged in the system. So let's take a look at the keys for just a moment. A natural question, again, is how do we control who has which decryption keys? And this comes back to the same access control mechanism from earlier, decentralized delegation. So I did a brief example of decentralized delegation earlier on in the talk, but I want to do a more in-depth example to make sure we're all on the same page. So typically in a system with decentralized delegation, the system consists of many different trust domains. In every trust domain, there's a set of resources that are typically organized in a hierarchy. And furthermore, there is some authority who has control implicitly over all the resources in the hierarchy. In this case, we're doing a smart cities example. So the levels in the hierarchy correspond to buildings, floors, rooms, and sensors. So now, if another principal comes along and needs access to, say, all the resources in one of the buildings, the way these systems typically handle that is that the authority signs a certificate attesting that the building manager has access to those resources. And then he can present that to anyone in order to prove that he has access. And this continues transitively. So if the lab director needs access, he doesn't have to go all the way back to the campus facilities manager. The building manager can directly grant him a certificate, and then he can present those two certificates together as a bundle to prove he has access to any subset of resources, and so on for additional levels of delegation. Now, this works fine in typical systems that use decentralized delegation, but in JEDI, we want to do end-to-end encryption. So simply handing out certificates isn't enough. We have to hand out decryption keys that can be used to actually decrypt messages. So what does that look like? Well, the campus facilities manager, as before, implicitly owns everything in this trust domain. So he has some kind of master key that can decrypt all the resources in the domain. Similarly, when the building manager needs access, he has to generate some key that only works for a subset of those resources and give that to the building manager, and so on for additional levels of delegation. So again, the key difficulty here is that we can't simply hand out certificates. We have to hand out keys that can be used to decrypt messages. So based on these high-level ideas, I'm going to talk about a first cut of JEDI, how we can instantiate these ideas using attribute-based encryption. And for now, let's set aside efficiency. I'll come back and address efficiency later on in the talk. So recall that we're going to encrypt the message according to the resources being published to. So in attribute-based encryption, you can encrypt a message using a set of attributes, where each attribute can be an arbitrary string. So in this case, we can encode the resource soda hall atrium temp into 3 attributes, 1 soda hall, 2 atrium, 3 temp, and use those 3 attributes to encrypt the message. Now we also have to figure out what the keys look like. And in attribute-based encryption, keys correspond to policies that check for certain attributes to be present in a ciphertext before they can decrypt it. So if we look at these 2 keys here, the key for soda hall / star that can decrypt all the resources beginning with soda hall, it has the policy 1 soda hall that checks for that one attribute to be present before it'll decrypt a ciphertext. Similarly, the orange key corresponds to the policy 1 soda hall and 2 floor 4 that checks for both of those attributes to be present. And a final property of attribute-based encryption we're using here is that given a key for one policy, you can generate a key for a more restrictive policy. And that allows us to generate the orange key from the green key in order to support decentralized delegation. Now I'm going to talk about how we can add a limited duration onto this delegation. So you can delegate someone access to some resources that expires at a certain fixed time. So the first thing that we do is that we encrypt using the current time alongside the resource name. So as before, we include the 3 attributes corresponding to the resource, but we also include 3 additional attributes describing the time at which the message is being published. In this case, year 2019, month August, day 16. And then we need to encode the limited duration into the keys, into the ABE keys, into the ABE policies corresponding to the keys. And we do that by recognizing time as being another hierarchy with levels corresponding to, for example, years, months, days, and hours. So if we want to generate a key with a fixed expiry date, like February 2nd, 2020, what we do is we take the limited duration and we express it as a time interval in this hierarchy. And then we decompose the time interval into a set of subtrees that exactly cover that time interval. And note that because we're expressing time as being another hierarchy, there will never be too many of these subtrees. The number of subtrees will be logarithmic the length of the time range. And now we can actually construct the key with the limited duration simply by assigning one ABE key to each of the subtrees and bundling them together. And together, these 4 ABE keys in this example provide access for the time range that we desire. So far I've talked about how we can achieve expiry, but now I'm going to talk about how we can take the scheme that we have so far that uses attribute-based encryption and make it lightweight enough to run on even resource-constrained IoT devices. And to make the discussion concrete, I'm going to introduce the Hamilton platform, which is the platform for low-power sensing that we use in our evaluation. The device is based on a low-power system on chip with a Cortex M0 Plus processor at 48 megahertz and 32 kilobytes of data memory. So this is much, much more resource-constrained than, for example, a Raspberry Pi. And the intended use case of a sensing platform like this is so that you can deploy it ubiquitously in, say, a building to collect ambient sensor readings for several years at a time. And in order to make such applications practical, we need to see several years of battery life, and the system has to be low cost. So we're powering it with a $1 battery. And for a sensing platform like this, it turns out that the limiting factor, the hardest thing to make a protocol like JEDI run on a device like this, turns out to be the power consumption of attribute-based encryption. So we're already making efforts to use attribute-based encryption rarely. In particular, we use hybrid encryption, which means that we first use a symmetric key, encrypt the symmetric key with attribute-based encryption, and then use a symmetric key for subsequent messages. So we only actually have to invoke attribute-based encryption when the attributes change. And that happens once every hour when the attributes corresponding to the time change when the time increments. But despite invoking ABE rarely once every hour, attribute-based encryption dominates the overall power consumption. And to put that in perspective, we measured that, we calculated that an attribute-based encryption takes 4 minutes to compute on Hamilton. And in and of itself, the 4 minutes isn't a problem because you can encrypt in the background to mask the latency and so on. But the power cost doesn't go away. And at 1 ABE encryption per hour, the battery won't even last 100 days, which is a problem because we want several years of battery life. So our first step is to choose a more efficient encryption scheme than attribute-based encryption. And the literature is pretty enormous here. There's a very large variety of encryption schemes we could possibly choose that all make different trade-offs between functionality, performance, and security. So we identify WKD-IBE as an encryption scheme that's more efficient than attribute-based encryption at the cost of being less flexible. Yet, we realize that it's flexible enough to instantiate JEDI if we use it carefully. So here's a summary of how WKD-IBE works. So in WKD-IBE, each ciphertext or key corresponds to a vector of strings and wildcards. It looks like this, where some of the entries are strings, others are wildcards. The rule is that a key can decrypt a ciphertext if their vectors match. And what makes this interesting is that given a key, you can generate a key where some wildcards are replaced with strings. So for example, if we had a key corresponding to this vector, we can generate a key corresponding to this new vector where we replace one of the wildcards with a string. So JEDI uses WKD-IBE in a very particular way, where we encode multiple concurrent hierarchies, one for the resource and one for the time, into a single WKD-IBE vector, which is interesting because the original intended use case in the WKD-IBE paper was generalized delegation within a single hierarchy, yet we're able to use it to encode multiple. So for example, if we have this resource prefix and this time range, we can encode it into a vector like this, where we're using the first few components for the resource and the last few components for the time. And then we can support decentralized delegation to generate a private key for a more restrictive set of resources and a more limited time duration simply by replacing wildcards with strings as follows. So in this way, we're able to use the delegation property of WKD-IBE to support decentralized delegation, maintaining the expiry and the resource properties from before. Now, using WKD-IBE instead of ABE helps a lot, but it isn't quite enough to reach several years of battery life. So we additionally make cryptographic improvements to WKD-IBE to make the scheme more efficient as used in JEDI. So here's the existing WKD-IBE encryption algorithm from AKN07, and it works as you might expect. It takes in the message, the attribute vector as inputs, and it outputs a ciphertext. Our observation in JEDI, however, is that adjacent encryptions using WKD-IBE differ in only a few attributes. And the way to see this is as follows. We only invoke WKD-IBE when the attributes change, which happens once every hour when the attributes corresponding to the time change. But even then, all the attributes corresponding to the resource actually remain the same. And furthermore, the attributes corresponding to the high-level components of time, like the year, month, and day, are changing rarely. It's only the last component, the component corresponding to the hour, that's changing on every single encryption. So our idea is that we develop a new encryption algorithm for WKD-IBE that allows us to do work only according to the delta from the previous encryption. So our new encryption algorithm would ideally look like this. It takes in the message and the attributes that changed since last time as inputs and outputs as ciphertext. Now, in order to actually make this efficient, we also output some cryptographic state that encodes the work we have done for the existing attributes and what the existing attributes are. And then we take in the previous state when we do the encryption that allows us to reuse some of the work from before in some sense and only do work according to the delta. So that concludes this part of the talk about JEDI's approach. There are also 2 additional properties in JEDI on anonymous signatures and revocation, which I don't have time to talk about, but you can see those details in the paper or come talk to me afterwards. Now I'm going to talk about our implementation and evaluation. So our implementation consists of 2 parts. The first part is our crypto library that implements WKD-IBE in our new encryption algorithm. It also contains assembly optimizations for Cortex-M0+, the processor used on Hamilton, which provide a 4 to 5x performance improvement over a pure C or C++ implementation. Second part is a prototype of the JEDI protocol, which we implemented for BW2, a messaging system for smart cities. So here are the performance results from running BW2 with JEDI applied to it. Most of JEDI's overhead, as you can see from the blue region on the graph, comes from the symmetric key crypto library that we're using. And furthermore, JEDI's overall overhead is only about 10 milliseconds for small messages, which makes it practical for smart cities applications. Second, we want to look at we want to evaluate our optimizations to WKD-IBE, how they affect the battery life on Hamilton. The first result here is that encryption with JEDI is 37 times more efficient than naively applying attribute-based encryption. Here's the battery life numbers that we measured by empirically measuring the current and the time it takes over encryption. So what we can see is that we don't quite get a 37x improvement in overall battery life because an improvement ends up being amortized by the cost of symmetric key encryption and sampling from the sensors using the network and so on. But we see a 14x improvement over attribute-based encryption in battery lifetime. We're within 2x of the battery lifetime using AES only, which we consider kind of an upper bound of what we're able to achieve. And furthermore, the battery life is several years long, so it's practical enough for the intended use case of this sensor, widespread deployment in a building. So one final point I want to mention is that we're collaborating with other researchers at Berkeley who are working in the smart city space to actually deploy JEDI in smart buildings. So you can see some sample data from a pilot deployment encrypted end-to-end with JEDI. We're hoping to continue this in the future. So if you have any interesting use cases, I'd be happy to talk about that afterwards. So in conclusion, JEDI is an end-to-end encryption protocol for large-scale IoT systems that allows senders and receivers to be decoupled as in publish-subscribe, supports decentralized delegation with expiry, and can run on devices across the spectrum of IoT resource constraints. So that's all I have prepared. Thank you for listening, and I'm happy to take any questions.
Hi, I'm Leah Kisner from Humu. You said, if I understood you correctly, that you're using one hierarchy for resources and one hierarchy for time. Does that mean that this is limited to each subscriber getting one resource?
No. So we're using one hierarchy for resources and one hierarchy for time in the attributes used for encryption.
Yeah. But the reason I ask this is if I give you resource A and resource B, and each of them has an expiration, but they're different expirations, what's stopping me from using the private key corresponding to a later expiration over here and just jamming it in this one?
That's an excellent question. The reason we're able to prevent that is because we're encoding the expiration and the time into the same, the expiration and the resource into the same key. So there's no opportunity to mix and match keys. So in fact, if you look at some of the other encryption schemes we could have chosen instead of WKD-IBE, for example, if you use hierarchical identity-based encryption, then you'd be able to mix and match the expiry and the resource. But given that we're encoding them in the same key, that isn't possible in JEDI.
Awesome. Thank you.
Hi, thanks. Regarding the motivation for this work, what's the occurrence of malicious or potentially exploited pub/sub brokers versus end IoT devices actually getting exploited?
So our motivation in protecting against the broker is that the broker, if it's not protected, consists of a single point of failure in the system. So what would happen is that sure, okay, you have a good point in that if an adversary compromises one of the IoT devices, they can see all the data that that device is interacting with. But they have to compromise all the individual IoT devices to do that. Whereas in contrast, if the broker is left unprotected, then if they compromise the broker, they can see the data for all the devices in the system. So that's our motivation for protecting against this particular use case.
And then are there instances of that happening in the wild?
I'm actually not aware of any instances with publish-subscribe. Part of the reality is that these large-scale publish-subscribe systems typically happen in industrial use cases, sure. And I'm actually not familiar with any attacks happening there, though I'm not sure where to find information about that, even if it were to happen.
Yeah, it might not be public. All right, thank you.
Okay, well, thank you. Let's thank the speaker and all of the speakers. It was a terrific session today. Thank you.